Hello, everybody. Thank you so much for joining us for today's LJC event with Alex and Rich. Let me introduce myself. For those of you who don't know me, my name is Abby. I work with the LJC and the other communities, all of which are free and run by RecWorks. RecWorks are a tech recruitment company, but with a big difference. So obviously, as a company, we're always on the lookout for more clients, and some of our best clients have come from community members who recommended RecWorks to their internal talent team. So if you're hiring for a new team or you're working for a company that is, please do let us know. If you want to know more about what we can offer, just ping me a message on Slack or LinkedIn. My name is, as you see it on the screen, and we really look forward to working with you and taking that forward. So what's the difference, I hear you ask? Well, we also believe that recruitment really can be a force for good in the industry beyond just placing people in jobs. We have a particular focus on learning, mentoring, and personal development, and that is where our communities come into play. If people want to learn and others want to teach or share their knowledge, we are more than happy to connect you through our communities and events. We see this as giving back to those we've worked with in the past, but also paying it forward to those we hope to work with in the future. To date, we have run hundreds of events for engineers and developers, students, graduates, CTOs, the list goes on. We've run conferences, lightning talks, hackathons, all sorts. Earlier this year, we made our 5,000th introduction through our Meet a Mentor community. That does what it says on the tin. You can meet a mentor or you can be a mentor as well. And we're really excited about how many connections we've made there already, and we're looking forward to even more. As I've already said, we love to give opportunities for people to connect, and this event is part of that goal. If you want to know more about any of our communities, please do get in touch with me or Helen Lewis if you know her, and we can take it from there. The recording of today's session will be available for you on YouTube. I will put the link in the chat channel for you once we've got started. And we've got a double bill for you, as you know, today. So what we will do is Alex has said he's more than happy for you to put questions in the chat as he goes along, so please do that, and I will keep my eye on that and hopefully ask questions at pertinent moments. And for Rich's talk, if you can save your questions and we'll have those at the end, just because of the way the talks work slightly differently, that would be amazing. But with no further ado, over to you, Alex.
Thank you, Abby. Okay, let me just share my screen. Where's it gone? There we go. Okay, so thank you everyone for coming along. So I'm going to have the joy of talking today about how do we start trying to take our kind of existing RESTful applications and actually try and use them as serverless functions. Now, serverless itself is an area of quite a bit of interest these days in terms of efficient compute models, resources when we need them, as we need them, without having to worry too much about, well, as much about the costs, say, as other, in particular, cloud offerings that we might be looking to run on. So for this talk, I am going to do quite a lot of background on serverless. There is very little background on REST, as I'm assuming most people here have an idea about some of the core bits around RESTful web services, APIs, that kind of thing. But obviously we will be trying to, towards the end of this, pull the two together and kind of show these as kind of a nicely combined concept. I will admit a lot of this material does actually come from Red Hat. They've done a really good job of actually kind of going over what is serverless, what is kind of function as a service and what have you, but I'll just go through some of those key points from their pieces. So as you can see on the slides, it is a bit dense at points just because there is a lot to try and understand about these things. So to me in particular, serverless is kind of a compute model. So while we talk about it as a cloud native development model, there is a degree of that, but it is about how do we most efficiently do compute in my mind. So it is very much a case of I have a request comes in, I want to do that request, but I then want any resources to actually hopefully not be needed anymore, and then I can just let those go and I'm not being charged by my cloud provider anything more. But also as part of that, I don't want to have to worry about what VMs am I running stuff on, what am I kind of some of my key infrastructure pieces, right? Serverless in theory, there are huge numbers of servers behind it, but I don't have to care about them one bit. And that is purely a developer perspective. Obviously, if I do need to think about what kind of operating system am I truly running on, and we'll come on to container as a service later as one of the kind of key offerings there. Well, obviously, you control what operating system your runtime's on, but kind of what's underneath you, you don't have to care about as much. But yeah, the core thing with serverless is trying to empower the developer to focus primarily, almost entirely on their code. So as I say, you don't have to worry about potentially what runtime you're on. So obviously, given we're Java, we say, I want to run on Java, but I'm not going to be as concerned about necessarily the flavor. And by that, I do mean things like OpenJDK, IBM Semaru, Amazon Corretto, all the various ones we now have these days to run on. I'm kind of going to give some of those decisions over potentially to the provider of the offering. And I just need to worry about, as I say, what my code is actually going to be doing as part of that. And obviously a key thing with serverless is that kind of scaling up and scaling down with the workload. So obviously within Kubernetes, you do have that concept of once your CPU or potentially your memory reaches a certain point, you will scale out to a certain degree. And obviously once things kind of ease off again, you can scale back down. But serverless takes that kind of to a bit of a next level, I would say, over what you get with Kubernetes. But there are significant similarities between them. And it has to be said, for all serverless offerings, it is still container-based, whether it's function, container, or anything else. It's just a case of how much of an understanding do you have of the infrastructure underneath you. And yeah, in terms of when it comes to that joyful time of the month when you've got to pay your bill, serverless does have the advantage of you generally do pay for only the things you've actually done. So if you don't have any workload for a month, your bill should be zero, hopefully, unless you've got other things obviously running as part of that. And very much serverless is an event-driven execution model. So whether that's HTTP, whether it's events from object stores or Kafka queues, is very much about taking those elements and then doing something with it, and then hopefully disappearing again if you can do so. Now, the most traditional view we all have of serverless kind of came along when Amazon released AWS Lambda with function as a service. So very much a very simple concept of you write a piece of code that hooks into a provider's SDK, and we will then do everything for you. So all you have to care about is your very small function as part of that. And that function is generally just a single unit of work. So an example of image processing. So if you want to do some image manipulation of something loaded into object store, so having loaded the file into object store, your function will be invoked effectively, told this is the file you're operating on, fetch the object, do whatever you've told it to do in there, and probably return it back to the object store, all as part of that single nice operation. And again, nice, simple, and purely that piece of code that you actually do give to, say, Amazon, Azure, that's all you actually care about, and obviously all the dependencies that relate to that. As I say, they are in particular for functions, really good for specialized functions. As I say, image processing is actually a really common one. Processing items off queue is another that you see a lot of, particularly for asynchronous. So typically, and yeah, so we will come on to event-driven architecture towards the end, but very much a case of going, all right, I've got a unit of work, thank you very much. I'll probably let you know when I'm done at some point in the future as part of my ongoing kind of finalization process. And yeah, being event-driven. So as I mentioned, you have Lambda is a well-known one. You also have Azure Functions and Google and IBM's Cloud Functions. For the top three, I will say they do all require use of their SDKs to actually be able to invoke your function. And they are all wildly different to each other. It is amazing the difference that they've managed to achieve for something relatively simple. Amazon is relatively straightforward in terms of how do you hook things up, regardless of actually the source of information as part of that. Azure is a minefield of you go through, oh, if you want to do HTTP, you need to add these files and you need to annotate your methods these ways. Google's a bit simpler than Azure Functions, but and kind of sits between two. IBM Cloud Functions, which is built on OpenWhisk, is actually a bit more helpful in that actually you don't need to do an SDK, but that means you actually generally have to deal more with just general HTTP workloads, regardless of actually the original source of that information. Another offering that has started to become more prevalent in terms of what is referred to serverless is container as a service. So this takes functions a little bit further in some ways, but we'll come on to kind of the similarities and where the key differences are in a little bit. So container as a service, I always look at it and kind of think it's a bit like Docker Compose in some ways, in that you're not at your full kind of Kubernetes, OCP layer of things where you have to worry about what's my ingress, routes, here's the services I need to worry about that. With container as a service, it is very much a case of here's my container, run it, and potentially setting up some additional piece of infrastructure if the offering requires it, to be able to then go and call it. Nice thing with containers as a service is you control a little bit more than what you had with the functions. So you can decide, I do want to run with, say, Amazon Corretto or OpenJDK or IBM Semaru as my JVM kind of choice. So it fits a bit more nicely with what you might want and gives you as a developer a bit more control over the functions. But also with it being container, again, you can control the operating system of your container. What's the size of your container? Because what's provided by, say, Amazon as their base image is actually really nice and small for Lambda, and you can build your own images off that as well. But again, if you do need a little bit more, say, with Java, you might need to actually put some additional binaries in there. Again, that's much easier to do with container as a service than trying to go down the function route, where you might need to do some interesting kind of models to try and get a binary in as part of your kind of jar package that then gets unpacked in an interesting way. So yeah, so container gives you a huge amount more flexibility than functions, but this is where you kind of start to see needing to understand a bit more as a developer with containers, while for functions, it's very much I just need to do this one thing and I can do that relatively straightforward. And yeah, it does give you also a degree of orchestration. So when I'll talk about things like Amazon Elastic Container Service or ECS, then you can say, or do certain things with your containers. So you can deploy multiple containers of different types actually with ECS, and basically say have your primary kind of instance that's, say, handling web workload, and then an offload pod instance even that you're sending some of the work off to from that kind of primary instance. So you can do, as I say, this is where you start to see it more like Docker Compose than, say, Kubernetes. But yeah, it is a much simpler platform to deal with than either Kubernetes or OCP, because it is just a case of here's my container. Oh, here's, so in particular for Amazon, again, you do need to create your load balancer to be able to call your container, if that's how you want your container to actually get its workload, if you via that kind of endpoint. But those are all generally fairly easy to set up, as I found recently, as long as you've got all the right permissions. Yeah, when you deal with clouds, number of permissions is like to describe a minefield is quite understatement, I think, for cloud permissions, especially when you're dealing with multiple components. Now, with containers as a service, you generally have two types of application, as it were. So you've either got a service or kind of a cron job style one, so run on scheduled timer or some other trigger. And typically with CAS, you are generally exposing an endpoint as the sole way to invoke your instance. So obviously, well, cron does triggers, services are HTTP regardless of the source. So with functions, you'll see really tight integration with the cloud providers' other kind of offerings. So whether that's their queuing service, object stores, all of those will generally have a way to easily trigger that function as part of the configuration, either of the function or the app or the kind of the producer of the events. As part of that. But yeah, CAS generally just focuses on HTTP, and generally you then need to have a look at, say, event brokers to get some of those kind of event workloads from object store to your container. The other thing with services is that they can scale by a few more metrics. So functions generally scale purely based on number of workload items. So Generally, functions also per instance will handle one event at a time. So if I say I allow my function scale to 10, then if I've got 10 items of work, then I'll have all 10 functions running. If I don't have 10, then obviously I'll be lower than that. And obviously there will be an element of queuing behind that. With CAS, you generally get more Kubernetes style scaling, so the standard CPU memory. So this does allow you to do a bit more when you do think about, in particular, RESTful services being able to handle multiple requests. So a function can quite easily be bogged down by the fact that while you might be reasonably quick at handling a one individual request, that can add up fairly quickly when doing the processing of those through functions. One interesting thing that is becoming a lot more prevalent, and we'll come on to, there are two kind of offerings that actually do HTTP scaling. But yeah, you can actually look at the number of HTTP requests you're receiving in a period of time and scale based on that. I will say scaling is entirely relevant to what your application is trying to do. If you are doing really nice, simple RESTful requests, then it might just actually come down to how many threads can you actually handle at a single time. So while you might have a low CPU threshold, right, the number of threads you can actually process in that time period might actually be relatively small. So you might actually want to scale on those HTTP requests rather than say CPU as part of that. But it all comes down to, as I say, what is your application actually doing and what is it, how often is it being used as part of that. And in particular, for containers as a service is really well suited to web apps. Well, obviously RESTful generally we find. Microservices, so not quite the full level of Kubernetes, but again, you can have these relationships between them depending on the offerings. So some are a bit more limited than others, and also doing large data processing tasks. So one thing you can find with functions is actually they're bound by time. So from, in particular, AWS Lambda, you actually have 15-minute maximum runtime of a function. So if your function doesn't complete in 15 minutes, it gets terminated, which can obviously be a bit of a pain, but this is where you can say, look at CAS as the alternative for those. But again, different vendors provide different levels of either tuning for some of these timeouts, but generally they do have somewhere a hard limit depending on how the interactions with external sources is done. Now, one thing to note about CAS offerings is not all of them are actually have kind of serverless qualities about them. So some, and typically this relates to you actually need to provision the infrastructure underneath them. So in particular, Amazon ECS, ECS, you'll see it pop up a bit later on as well. So raw ECS, you actually need to provision EC2 instances underneath yourself to actually run your container instances. So this is ECS in its raw form. So again, because we're actually now having to deal with the servers, it's not serverless. You also have Azure container instances, which again, the scaling and how it does that doesn't quite match generally what we're after for a serverless application. Now, there are several CAS offerings which do provide these serverless capabilities very similar to functions in terms of how they scale, or the fact that I at no point know what servers I'm running on whatsoever. I just know that how my app will scale and what bounds I put on those, and the provider will just handle all of that for me. So ECS with AWS Fargate does actually abstract away that server management aspect for me as part of configuring it. So yeah, with ECS, you can do serverless. You just have to use the Fargate type when you're doing your deployments. And then you've got a few others. So the ones I've called out here are Azure Container Apps, Google Cloud Run, and IBM's Cloud Code Engine. So in particular for Container Apps and Code Engine, they use two CNCF projects as kind of their underpinnings for how they then do their scaling. So Azure and particularly Microsoft have backed KEDA. I'm hoping I pronounced that correctly. And IBM has gone with Knative as their choice for what underpins them both. And both of those do support a range of scaling metrics. Knative is relatively simple in that it does just generally do CPU memory or concurrent HTTP requests. KEDA actually has huge range of customization available. And if you actually go and have a look at them, I do have a link at the end of this. They actually do allow, and you'll see lots of other say providers actually do provide their own custom scalars. So based on metrics that they understand from their own kind of workloads, they'll actually scale on that. So I know there's a scalar for ActiveMQ. So kind of based on the number of messages you have on your queue, it will scale based on that, not just kind of a basic set, which say generally Knative and the other offerings go for. Fargate itself, very similar to Knative in that it's CPU, memory, HTTP, and Cloud Run again is the same kind of metrics that it's using for those. Now, one thing that we generally have kind of this attain goal towards, and I have to say, thinking about Java is actually one of the biggest challenges because Java has this beautiful JVM underneath it that requires startup and warm up and getting itself into a state where it's actually started and then started our application. And part of that is having a look at scale to zero. So scale to zero is obviously the ultimate goal with serverless and serverless applications, is that we can have 0 running instances when there are 0 workloads. Now, FAS does achieve that. And that's because you've got this nice hidden kind of architecture and infrastructure in front of your function that basically means that it can sit there, accept a request and go, yeah, once your function is ready to run, I'll send that on to them and then they'll process it and I'll get a response and do what needs to happen next. Yeah, for in particular CAS, then that again depends on what the underlying kind of infrastructure provides to you. So both as container apps for Azure and IBM Cloud Code Engine and actually Google Run, they all support scale to zero. So they can scale down to 0 when nothing's coming in. And when they get that first HTTP request, they will then spin up our instance and then start serving that request. ECS with Fargate actually doesn't support scale to 0 for any scaling metrics at this point. You have to have at least 1 running instance to be able to receive any requests on there. As I say, in particular for that instance of 0 to 1, so basically you've been sat there cold for a little while, you get that first new request in, and particularly for Java, if you're running with just a standard JVM, then it can have a notable impact in terms of that initial performance. Obviously, once you're up and running, then you should be all right. And one of the differences, say, between function and CAS is a function will be, as soon as there is no work to do, it will just stop. With CAS solutions, generally you'll find that there is a kind of a tail off period after the end. So once it's returned the request, it will sit there for a period of time, basically waiting to see if there is more work to come in. And if not, it will then scale back down to 0. And also one other consideration you have to make is where is your container image actually hosted when you're putting it in. So if you're hosting your container image, say in the US, and then trying to bring it up in a, say, a European data center, that has an impact if it hasn't got that image cached locally. And hopefully when we do the demo, you'll actually see some of the impact of that when we have a look at that. So just to bring kind of an overall cloud picture together with what I've just been talking about. So having a look at the general as a service picture for cloud offerings and what do we as developers own, which is kind of that those user management boxes versus what the provider gives to us. And also what are we looking to scale when we're looking at doing these things. So I won't dig into too much here, but as you can see, one interesting thing actually about CAS is that it sits in between IaaS and PaaS, while function as a service is a bit more off to the side as part of that. But here you can see what, again, I was trying to convey how much control we have over that. So with CAS, we've kind of got control pretty much to the level I would say most of us are actually getting more used to these days, in that we build a container, we hand it off to someone to go and run somewhere. And obviously, generally, one of the nice things with Java is it's really easy to hand that off to someone and just go run that wherever you want, without having to worry too much about anything that's underneath you as part of that. So let's do a comparison of FAS versus CAS. So in terms of one of the key things generally we've always tried to achieve with Java is, can we move our application from environment to environment with no changes whatsoever? And I have to say, for FAS, and in particular when you have a look at Java examples for all the offerings, it's really hard to move those between the various offerings without having to basically put in, say, some third-party libraries as part of those. And yet, as I said earlier, all of their SDKs are really unique to each other. So Amazon is actually quite nice in that you just do an extend of a particular class they provide, and you just do a bit of configuration in terms of saying, I'm going to accept, say, a S3 event, and I'm going to send back a HTTP event if you so chose. Really nice, simple. All the actual linking together is done outside. If you look at Azure, you have to do a ton of annotations to say, I'm going to be accepting even a HTTP event as part of that. You actually need to supply, I think it's about 5 or 6 lines of JSON to actually do routing information to get to your function as part of those kind of offerings. So very different approaches as part of that. With CAS, because it is built from the container and how they are being exposed as part of these provider offerings, they are really easy to move place to place. So, I mean, I've run the same container basically in IBM Cloud as I've run on Amazon ECS. Had to make no changes whatsoever to those. It's all about what I'm putting in place within those individual providers as part of that. And that does relate again to the lift and shift as part of that. Functions do need a lot of rewriting, adapting, and potentially the use of third-party libraries to actually move into these offerings. CAS, you containerize it, you can move it anywhere. So in terms of the libraries I am referring to, so some of you may be aware of things like Spring Cloud Functions. So they're very much a way of, say, doing HTTP workloads in a way that is agnostic to the cloud providers. So effectively, effectively addresses the portability issue of those. So you can just say for Spring Cloud Functions that, okay, I'm in AWS, I just need to bring in the AWS kind of underlying library. That actually, in terms of what I'm writing, is the same across all of them. As part of that, you also have Quarkus do quite a set of libraries around these functions to be able to actually, Quarkus allow you to do RESTful, servlet, as well as their own funky. So that's funky with a Q rather than a C, which again is cloud agnostic, but again is to try and help people be able to move, say, between Azure functions, AWS, Lambda, Google Cloud Functions on there. But yeah, most of these are kind of irrelevant for CAS. You can just lift and shift your application and just stick it in CAS, like we've a lot of us have started to do for kind of existing applications. Runtime, I've already kind of covered that to a decent degree. And in terms of flexibility, yeah, you have a lot more control with CAS because you own that container image. While in a function world, generally speaking, so Lambda actually does allow you to do your own containers, but you have to meet a lot of their own requirements as part of that. But yeah, you have a much more limited set of availability. And yeah, in terms of frameworks, yeah, for CAS, you just use Spring, just general Spring, so Spring Boot, Spring Web, any of the other well-known ones. So RESTful, obviously, JAX-RS, things like that, do work in CAS. With FAS, you generally either need to use a specialized framework to actually allow you to use, say, JAX-RS, as I mentioned, Quarkus. You actually have to use a kind of a library they provide as part of that, or again, they are very specialized. So there are well-known Python frameworks like Zapper, very much is geared towards AWS Lambda as its kind of runtime environment as part of those. And then instance lifetime. So you can configure some function as a service offerings to, in theory, have an unlimited lifetime, but in reality, you ideally want to do minutes. So yeah, so for 1 minute, I think that was Google Cloud Functions. Basically, for a standard HTTP request out of the box, it has to respond within 1 minute. You can increase it, but yeah, you can go up to about 60 minutes generally for HTTP workloads, which obviously is interesting because then your app, from a consumer perspective, you have to be aware that you might be waiting an hour as part of that. But yeah, for CAS, you have much more control over what your kind of runtime is going to look like as part of its lifetime. So you just generally say, this is my base workload for what I want. So if you do want kind of millisecond response times, then generally speaking, you'll always have one instance running. So given I am from IBM and Open Liberty, our main openliberty.io site, we are running on IBM Cloud Code Engine, and basically we can't get the performance we need for that if we from scale to 0, we actually do need one running instance to give us the millisecond response time that we're after as part of that. But you have much more control over how it does do its scaling, as I say, based on the various metrics we covered before. So now thinking about, obviously the title of the presentation was about running REST as serverless functions. Now, hopefully through what I've just gone through for both FAS and CAS, you've got the idea that primarily we're going to be looking at CAS for how we're going to do our RESTful kind of web services. And that's because actually, and it has to be said, RESTful actually does map quite nicely when you think about it into serverless functions, right? Both are supposed to be stateless. Functions, and when I say functions, I do mean general functions, not function as a service here. But it's just a good way to actually think about what we're trying to run as part of this, in that very much they have to be generally single units of work, and you do have to think that every single request actually might be hitting a different instance. And by that, I do mean potentially the instance you hit on one request might have disappeared and a new instance spawned by the time you make your next request. And even with load balancing, you will end up with kind of a round robin view of requests coming in. So you can't do, say, sticky sessions, as I've found with some other Java kind of web servers when I've worked with them, in terms of making sure that you're able to actually continue on with effectively the same session as part of that. And yeah, in terms of actually doing the lift and shift, CAS, because it generally everything is exposed as HTTP already, really nice and easy, because it's just as long as we know what our endpoint is, and obviously with RESTful, we generally define what our paths are going to be, then there is a really nice match between those two as part of that. And one of the nice things when you think about RESTful and HTTP as your main point of interaction with your serverless functions is obviously we have an application here that can have multiple paths. Therefore, it has, in effect, multiple functions within the same application. And one of the issues that some people have with FAS is actually the dependency mapping, because you generally can have very small items of work actually with big dependencies. And I'm sure many of us have had a look at Node and how many dependencies you can quickly rack up inside of a couple of minutes of adding just one or two dependencies for your application in there. So we can just host all of these functions, as it were, in a single application, in a single instance, running with all this serverless niceties in terms of management, of scaling. And we're already using the benefit, one of the key aspects of REST, of the HTTP, basically telling us where our workload is going to go. And also, given obviously how RESTful has been built and all the technologies we have to host our RESTful services, you can host multiple handle multiple requests, before we have to worry about scaling. So from a code engine perspective, we'll have a look at that and how we look at HTTP and how many concurrent requests before we have a look at scaling. So before we jump onto the demo, let me just quickly check. So the question from Maya, sorry if I've got that wrong. So can we consider CAS as a microservice? You can do. I mean, as I say, it depends on the provider. So with Amazon, you can have, when you bring up an instance, you can deploy multiple microservices as part of those, and those interact kind of under the covers inside of your virtual private cloud. With Code Engine, it's very much you stand up an instance, and obviously while you scale those out, there isn't any interaction between those. But you can think of them in very similar to microservices, in that obviously it should be really nice and small. You don't want monoliths, really don't suit any of these platforms because they are far too heavyweight and will cost you quite a bit of money when you've got monoliths deployed. Microservices, obviously in theory, nice small footprint, memory, CPU. So you can, you'll see a lot of papers talk about microservices with CAS as part of that. And in terms of interactions between them, then it comes down to, certain providers give you different kinds of offerings on there, depending on what type of technology stack they're using. But if you need clarification, do just say if I've missed anything as part of these questions. So demo time. Go on. There we go. Okay. So for this, we're going to have a look at IBM Cloud Code Engine primarily. Obviously, given we are doing this talk from IBM, and this was one of the easiest ones we've had to actually set up as part of our kind of the work I've been having a look at for microservices. So Code Engine is technically you do, so obviously you need an IBM Cloud account. You do need a credit card. However, there is a free tier for it, so you can have a play with it without actually having any money charged for it. But there, obviously, you just need to watch on workload as part of that. So within this, you have the concept of projects and then applications within those projects. So I'll have a look at my getting started one in a minute, but I'll just have a quick walkthrough of kind of the create process as part of these. So with most offerings, so I'm not going to bother with changing name for now because I won't go through creating it at the end. Is you can start with 2 points within these. So you can either use a pre-built container image, and most of the container offerings actually do support a raft of container registries. So you don't have to use, say, IBM's container registry or Amazon's container registry for these. You can just reference anyone there and do that securely as well. You don't need to have to worry about, say, oh, I have to use Amazon because security. You can supply the kind of the Docker pull secrets as part of the reference on here. Now, one of the key things that you'll find as part of the definition, so actually I do want this, is the listening port. Now, what you'll actually find interesting in terms of most CAS offerings is actually internally, the connection between effectively the gateway and your container is actually done by HTTP. And this is to make sure that, well, to make sure you don't have any certificate weirdness going on between kind of the gateway and your container. Everything up to that gateway is HTTPS enforced, but then from gateway onwards is actually HTTP. ECS actually does allow you to do both HTTP and HTTPS as part of those, and obviously, again, you can configure certificates as part of these of that, but here we don't want to worry too much about it. I've forgotten what the registry was, but yeah, so if you did want to do source code, then you can do that from GitHub, and basically it understands a range of build tooling, so things like Gradle, Maven, and also build packs. You can use those to basically build your container, and then that gets hosted. Obviously, if you're building from source, it will end up in IBM's Cloud Container Registry as part of those. And I have to say, building is generally part of all the cloud offerings that you'll find. The only thing to be aware of if you go down that route is you will be charged for the build time as part of the image build process. So it is a good way to save if you build in your own infrastructure and then publish outwards to these. Endpoints, so very standard, so public, private, project. So public obviously is going to give me a URL that I will be able to call. Private means that only within my VPC kind of concept will I allow requests to come in and out. So again, very standard across all the cloud providers. And then project is even more scoped down than private. So within private, say if I had an app, say running Kubernetes, that's obviously within my the same cloud account, I can then make a call to this service. Now be accepted, but I couldn't say call from my laptop to it directly. And again, project only does allow you to talk between kind of various ones. So coming back to the microservices, you can do it. And obviously that is you using the full URL you come up with the end. Then we go into some of the interesting bits that we have to worry about, in particular for Java, I would say. So obviously scaling instances max to min. Obviously, you do have to think about what happens when I'm scaled out for a long period at my maximum number of instances. Am I happy with the potential bill I'm going to end up with that? But then obviously that then comes back to, because you get charged primarily on CPU time, is how much CPU you give it. Through my playing around with this, I've generally found that for Java, you want at least half a CPU, and that's true for both Code Engine and ECS. If I had it less, it would eventually start, but it was quite a painful experience, it has to be said. If it was below that, kind of that half CPU kind of gave me just enough to make it a legitimate piece of experimentation. And as I say, for Code Engine, we actually look at how many concurrent requests do we have that can be going on before we look at scaling. So here, if I have 100 requests that are hitting one instance, well, when I get close to that, I will actually start scaling out horizontally. And obviously, if that keeps going, then I'll wait until I get to the max as part of that. You can read more if you look at Knative around this target versus max values on there, and obviously how long I'll take time out on those. So that's very much a gateway setting. And as very similar to Kubernetes, as you can do with any containers, you can set a number of environment variables as part of that. So if I take a look at my existing application, so this one I've had running for a little while as part of this. So this is using the Open Liberties Getting Started application. So I have been playing around with certain elements of this over time. As you can see, you've got no instances running. So again, so port 9080, which is Liberty's default HP port. Not too much interesting. So yeah, so that's my current image hosted instance. And then here you can see what memory, how many instances I scale up to, and some of the other details as part of those as well, and a few generated elements. So that CE relates to what's known as CloudEvents, and we will get on to CloudEvents hopefully. I'm just having a look at time, running a bit late, but anyway. Okay, so obviously here I've now got my URL, and obviously I know what my path is. I can do custom domains or use, say, a proper load balancer in front of this to actually give me extra layers of protection if I felt that was needed as well. And obviously it's a little bit hard to say in some ways with these container offerings to actually cause overloads of systems that you can say generally actually get with Kubernetes as part of that. So I'm going to make a request to my application. Now, the last time I ran this was yesterday. So hopefully this is actually relatively cold. So we'll be able to see actually kind of the performance that we get. So this is a raw JVM with OpenLibty with a simple application, but you'll see, so actually I should have started that. So hopefully this will kick into life in just a second. So yeah, so you'll see, so hopefully it'll kick in a minute. So it does take a bit of time to get warmed up as part of this, but once you've actually got that image, and if you're running it often enough, then generally it will stay in local caches as part of this. And if I remember rightly, my container image is actually hosted in London, while my instance is actually running somewhere in the US. So here you can see that my instance is now started up. So obviously you can see it's still kind of in that warming up phase of the JVM, because all I'm looking at here is just the instance count I have. So I'm not having a look, say, into the CPU usage or what have you. Okay, so now we can see that it has now responded, and I've got a nice mislead. So this is a RESTful endpoint we exposed, so you can have a look at the Getting Started GitHub repo, or our guide kind of takes you through a lot of this stuff. It is really basic, and I know everyone's here far more advanced, but if you did want to see what I'm running, then you can find it from here. So this will now carry on for a little while, kind of waiting for any more requests to come in. And when it doesn't need to, it will scale back down again. But given I've got about 15 minutes left, I will crack on with the presentation. And then we'll come back and have a look at what happened with the graph. So there we go. So when you do think about running in serverless applications, and in some ways to do with RESTful, you do have to think about how much resource you're going to give it from that base perspective. So how much CPU memory, while obviously considering that runtime that we're in. Because obviously, as I say, with Java, we have this runtime cost, And obviously there are things we can have a look at doing to get over those, and I'll come on to those in the next slide. What we're using for scaling, again, based on the provider, based on some of the rules they have. So with Knative, it's actually really easy to kind of understand that once I get to that 100 concurrent requests, I should be scaling. With ECS, it's how many requests in a given period of time. And actually, yeah, while I've scaled out on ECS, it was a bit hard to actually work out when it was making decision points, because I think it was basically a sustained workload over a 3-minute period, was what I managed to get working in the end. As I mentioned earlier, you do have to think about your requests interacting with other instances, either just because that request might go to a different instance because of scaling, or the instance that you're talking to has gone away and obviously new ones come back in its place. I have to say caching. So obviously if you can pre-warn caches, then that's really good for some performance from a web app point of view. But also if you do need to do caching, you might want to have a look at doing that externally to the application and the container, as opposed to doing it inside, such that you're not losing any of that information if instances are scaled down again, and then any external resources that you need. So object stores, messaging solutions, databases in particular. And the reason I mention those is quite often, in particular for, say, object stores, you might have to use different dependencies to do workloads. So for object stores, one, IBM and AWS both support S3 as their kind of object store APIs. Azure, Google all have their own APIs, their own standards. So you do have to be aware, if you are wanting to look at portability, if you're dealing with object stores, you do just have to be aware that some of those areas might become a bit challenging, because you'll need to put in all these different dependencies at different times, and getting that to work can be of interest. And also, as you could see, what's an acceptable response time to your request? It took a good while for that first request that I made to come back. As I say, for Open Liberty, we need millisecond response time. So as I say, so I was scaling from cold for 0. Naturally, I've had over a minute waiting for that to come up before. That was relatively quick. But yeah, so that's just general key considerations, I think, for moving to, in particular, CAS. Some of these, again, do apply when you're running as part of, say, functions as well. So from a Java perspective, what do we need to consider, and what can we have a look at doing? Now, with JVMs, there are a few interesting things starting to come out. So you've got GraalVM from the OpenJDK folks, which basically compiles your Java into a native application. So much closer to C than obviously we are generally used to. That gives you really good fast startup times, because you don't have any of those have pieces, as it were, that you need to kind of warm up that you have with Java as part of that. So that's the native route. And now you've got two interesting ones. So we, as IBM, released what's known as Semaru with Instant On with Open Liberty, which basically uses new kernel-based capabilities to effectively snapshot a container during its build and startup process. So we actually have a look at that and snapshot the container at a particular point during its startup period. And that can include app startup. So you can effectively start a container with a running application potentially as part of that, depending on certain things you might need to do. And then AWS have, through Lambda, recently announced what they call SnapStart, which is very similar to IBM's Instant On. Again, so that's based around kind of Amazon Corretto technology, and again, doesn't have a lot of the limitations that you'll find with Graal. Graal gives you performance, but sacrifices quite a bit when we think about it from a Java perspective. I won't go into that. It's best kind of read around, and Graal themselves talk about it. But yeah, so there are some interesting technologies coming in that are looking to address a lot of these startup issues that we have as part of that. And obviously anything we can do within our container to keep it small, as I mentioned, co-locate to where we're running it if possible, anything there to just try and make sure all these small things add up. And it is very much a marginal gains kind of mentality you have to have around kind of Java startup time within kind of serverless applications. And it's certainly one area that is of interest, I think, to a lot of people. CPU, I broadly mentioned this, but you do have to think about in terms of that startup period, because that is when you are almost certainly going to be your most CPU intensive period. But that also does then impact potential scaling. So if you did give it 2 CPU, but your workload is generally running at half the CPU, but obviously that half CPU, you might have other contentions within your system. So do consider those. And again, instance memory versus JVM heap, kind of a very simple one to think about. So kind of as a broader level, so kind of taking it up, we can start to have a think about what kind of architectures does serverless environments fit in. And one of the key ones, and one thing that gets mentioned a lot, is this event-driven architecture. So it's very much a software design pattern. Again, admittedly, as it says, kind of built around an event, and an event is really just a record of something that happened somewhere, but also is a mutable, as in this is what happened to this object kind of thing. So yeah, so for object stores, it's generally I wrote a new object, or I wrote to an existing object, or I deleted an object. And again, you'll find that with all cloud providers, all their different producers of events, so as I mentioned, and I mentioned a lot of those before, you can end up with, they are very specific to the provider and in terms of the granularity that you'll see from those. Now, one of the interesting things is what an event can be. Now, it can be a RESTful request, actually. So HTTP is itself considered an event, and that you are making some kind of request, or as another example, as already mentioned, kind of an object store deletion, and that can come through. And serverless is seen as kind of the ideal compute component within this overall architecture for handling of these events. Now, obviously, you can do that through long-running systems, but obviously, if you've got a period where you're doing very little workload, not having to worry about servers, not having to worry about as much about the scaling aspects of these things, makes it easier for us potentially as DevOps to actually run these applications cost effectively. Now, one key thing around event-driven architecture these days is actually what's known as CloudEvents. Now, CloudEvents is a specification that came out several years ago that basically provides an envelope around these requests and basically provides you with a set of headers and it kind of metadata about the event itself that you can then use to understand the event and then go and do follow-on entities from those. And CloudEvents is used by every cloud except AWS. AWS have AWS events, and they decided not to do the cloud event stuff. But yeah, so if you are interested in having a look at doing events driven kind of processing within Java, CloudEvents is something I would definitely recommend looking into as part of it, given it is quite widely proliferated, as I say, except for AWS. And the cloud events are actually by a Java SDK, which by a range of transports. And in particular, given obviously this is a RESTful talk, there is a RESTful web services package that allows us to both read and write cloud events within our application. So you can just say, here's my endpoint, and it accepts a cloud event. And then you can go and handle that cloud event as part of that. And the way most clouds do the transmission is via Event Grid through their brokers. So Event Grid or Event Arc is 2 examples. And those are almost solely sent by HTTP to kind of CAS offerings. So they allow you to say, this is the URL, or this is the kind of CAS object that I want you to send this to, and here is the path I want you to call on it when you send this event to me. So there is some good overlap starting to appear now around this event-driven architecture and actually being able to handle these events in kind of a RESTful manner as part of these. And yeah, event-driven architecture very much is designed to be asynchronous, which is a bit of a challenge when you're doing stuff via REST and HTTP, given you generally want to say, yep, no, I've handled that, here's my response. Because obviously a lot of events, all you need to do is basically say, thank you very much, I've accepted it, nothing went wrong, carry on going. But anyway, so that is a quite a bit of a blast through kind of RESTful with serverless. As I said at the start, there is a lot more you need to think about from a serverless perspective these days than actually from the RESTful. As I have to say, the industry from a compute perspective has actually kind of moved in a direction that has made RESTful actually a useful technology to be able to use in serverless environments. So thank you very much for listening. I have about 4 minutes for a Q&A.
Excellent, Alex. Thank you so much. I know we have had a question or two in the chat, but just in case anybody has any questions, do put them in the chat, or if you want to unmute and ask, please do. Like Alex says, we've got a few minutes, so we can do that. I'll just give it a couple of moments in case anyone's mid-type. Alex, I've got a question actually. If anybody wants to know anything further or discuss this with you, what's the best way to get in touch?
So probably the best way is either my email address. I'll stick this in the chat as well. So I'll stick my contact details in the chat for anyone who wants to reach out to me. So either LinkedIn or email is generally the best way to go about it.
Great, thank you. I am going to take it then that we don't have any questions. We've had a couple of comments saying really useful, thanks so much for your talk. So that's always good to know, isn't it? That obviously what you've shared has been helpful for somebody. So that's really exciting, thank you. What we'll do, if you need to have a quick loo break or make a cup of tea, I'm going to give it a couple of minutes just to do that. And then we will get going with Rich's talk. So I'll start Rich's talk bang on 2 o'clock, so that if you want to get yourself a quick break, you can do that. So I'll see you back here in a couple of minutes. Okay, thank you, folks. I can see we've got some more messages to say thanks for the talk and awesome presentation. So that's really cool. Thank you so much, Alex. And now, obviously, our headliner is Rich. So over to you, Rich.
Hello. Yes, I also loved Alex's presentation. Let me go ahead and start my video so you guys
Fabulous. Thank you.
And I will share my screen. Everyone see me? See the screen?
Yep, looks good to me.
All righty. So my talk today is called The Next Frontier in Open Source Java Compilers, Just-in-Time Compilation as a Service. So that's me, Rich Hagarty. I'm based out of Austin, Texas. It's a pleasure to be here with you today. So let's get started. I typically don't know the audience for these presentations, so I'll start at the very high level here. We're all Java developers, so we know what a JVM and a JIT is, but just so we're all on the same page. At high level, the JVM, the Java Virtual Machine, executes your Java application. The JIT, or JIT as just-in-time compiler, compiles that code into machine code, so it executes a lot faster. So with that in mind, we're going to talk about this concept of JIT as a service. So the basic problem, especially in a cloud environment, is Java running efficiently. It's bad, especially for microservices, or I'm not going to say bad, but there are some issues with it. And the underlying reason is the actual JVM and the JIT, which is great technology, but does have some issues, especially at startup, which I think Alex talked about a little bit. And then we're going to talk about a potential solution, which is JIT as a service. So is Java on cloud a good fit, especially in dynamic architectures such as microservices? So to get some context, let's talk about legacy Java applications, which were a monolith running on a dedicated server. To avoid any potential performance issues, we always loaded it with plenty of CPU and memory. Never went down, rock solid. Updates are very difficult, need to be planned out, tested. So upgrades usually happened every 6 months to a year. That's how we used to live. Okay, a number of microservices talking to each other, each running in containers managed by some cloud provider and some orchestrator such as Kubernetes. And we have auto scaling to meet demand as it goes up and down. So the main motivators behind going to the obviously flexible scalability, easier to roll out new releases. We've divided our services up into all these microservices so we can attack and update services without affecting others. And once we're on the cloud, we can take advantage of all those great latest and greatest cloud technologies such as serverless that come out. We have less infrastructure to maintain and manage, and potentially, or in theory, we want to save money. But this is hard to get right. So we have to always weigh performance versus cost. So on this graph here, lower left, we have containers that are too small. We don't run enough instances. So the cost is very low, but performance is unacceptable. Then we move to the top right. We have containers that are too large. We're running way too many instances. Performance is great. We're obviously wasting a lot of money. So we want to get to that quadrant in the bottom right there, where we have our containers perfectly sized. We have just enough instances to handle demand, but this is very, very hard to do. And why is that? Well, in order to figure that out, we need to go dig a little deeper and talk about the JVM and the JIT. So again, great technologies. The JVM has been around for over 25 years. It's one of the reasons that Java took off. You have this concept of write once, run anywhere. And the JIT produces very optimized machine code. The JVM deploys profilers to look at your code as it's running. It creates very, very optimized machine code, more than you can get doing a static compile beforehand. The JVM has very efficient garbage collection. And the longer your Java application runs, the better it gets. Because the JVM is collecting more and more profile data, the JIT is compiling more and more methods. And we call those methods that are identified as needing to be compiled as hot methods. So now some of the downsides of this process. That initial execution run is interpreted. So that bytecode that you're running, that Java bytecode is executed byte by byte, which is relatively slow. Until those hotspot methods are compiled by the JIT, it's going to be running in that slow method. The JIT itself can create CPU and memory spikes. Those CPU spikes cause lower quality of service, meaning performance. Memory spikes cause out-of-memory issues, which can include crashes. The number one reason, or one of the main reasons that JVMs do crash, is because of out-of-memory issues. This obviously leads to slow startup time and slow ramp-up time. And the difference between the two is that startup time is the time that your Java application takes to get to the point where you can actually handle a request, typically by interpreting the code. The ramp-up time is the time it takes for the JIT to compile all the hot methods that have been identified and get to that optimized state. So here's an example of some charts of CPU usage and memory utilization. As you can see, all the spikes happen early on in the process, and that is because of the JIT. Again, on the left, the CPU causes quality of service issues. The memory spikes cause out-of-memory issues. So again, looking back at that cost versus performance, that quadrant we're looking for, finding that sweet spot, it's all about provisioning those containers to the right size and also having well-behaved containers that can be efficiently auto-scaled. And we're going to get into that a little bit more. So for container size, the main problem is, or the main issues you're going to run into is you're going to have to over-provision to avoid these out-of-memory issues. And this is actually very hard to do. The closer we get to perfection, the harder it gets, because JVMs are non-deterministic, meaning you can run the same Java application multiple times. You're going to get different spikes at different levels. And looking at the graph at the right, let me see if I can turn on my little pointer. So you can see we have to allow enough memory for these spikes, but once it gets to steady state, it's going to be running at this level, and all this is going to be wasted. Now for auto scaling, we're going to be impacted by startup and ramp-up times. The longer it takes to start up, the less effective your ability to auto scale is going to be. And also CPU spikes can cause autoscalers to cause false positives. Alex touched on this. One of the metrics for scaling can be CPU utilization. Now, if your container starts up and initially runs through a number of JITs that causes CPU to spike, your autoscaler may determine that we need more instances, which is the incorrect choice, obviously. And you're going to get a lot of thrashing as a result of that. So in order to solve this issue, we obviously need to minimize or eliminate those CPU and memory spikes, and we must get faster startup and ramp-up times. And that leads me to JIT as a service. So the concept here is we're going to decouple the JIT compiler from the JVM and let it run as independent processes. As you can see here, we have our JVM's clients running on this side, talking to remote JITs over here. These were all treated like microservices, so they're handled by Kubernetes to make sure that we have enough instances running. And this solution is sort of a mono to micro solution. We've taken that monolithic JVM and we've divided it into two microservices, one being the remote JIT and one being whatever's left in the JVM. And you notice we have the JIT crossed out here. The local JIT still exists, so that if communication goes down to the remote JITs, we still have access to our local JIT. So essentially, we're treating the JIT compilation as a cloud service. So this feature actually does exist. It's called the JIT server, and it's a part of the Eclipse OpenJ9 JVM, also referred to as the Samru Cloud Compiler because it is a part of the Samru Runtimes distribution. And OpenJ9, if you're not aware, combines with the OpenJDK to form a full JDK, totally open source and free to download. Here's a link to the GitHub repo. So if you're not familiar with OpenJ9, it started life as the J9 JVM from IBM over 25 years ago. IBM determined early on that Java was becoming very popular and they wanted to ensure that it worked on all of their devices, handheld scanners all the way up to mainframes. So they wanted to ensure that Java worked on all of their products. So it can go from very small to very large footprints. It can handle constrained environments. It's renowned for its very small footprint, fast startup and ramp up time. And again, it was open sourced about 5 years ago to Eclipse, but it has a long history of success. Fortune 500 companies running enterprise Java have been using this for years. Now, on its own, aside from the JIT server, here are some performance graphs with comparing OpenJ9 against Hotspot, another obviously popular JVM. OpenJ9 is in the green, Hotspot is in the orange. We have tests showing that we can save up, we can get 51% faster startup time using OpenJ9, 50% smaller footprint after startup. And as you can see here, faster ramp up time with OpenJ9. And even when we get to full optimized state, we have a 33% smaller footprint than Hotspot. Whoops, wrong button. So I mentioned IBM Samru Runtimes. That is it is an IBM distribution, an OpenJDK distribution that comes with the Eclipse OpenJ9 JVM. In fact, it's the only distribution that does. It is at no cost. You can download it for free. It's stable, secure, high performance. Of course, it's going to be, IBM puts its name on it. It comes in two versions, two editions. It has an open edition and a certified edition. The only difference is the licensing and the platforms that are supported. And if you're wondering where the name Samru comes from, that's actually the Mount Samru is the tallest mountain on the island of Java. So that's the relationship there. I'm sorry, I keep hitting the wrong button. So from a client perspective, the JVMs that are going to be accessing this new JIT server. So let's take a look at some of the benefits. So from a provisioning standpoint, it's going to be very easy to do, or it's going to be easier to do because we only need to care about the application. Again, if you need to provision a container that does not have this JIT server, you need to take into account those peaks and you need to do a lot of load testing to determine what those actual amounts are. Obviously, you can just double the size of your container to take care of all the issues, but you want to get that down as close as possible when you're trying to save resources and save money on the cloud. So this makes that whole effort a lot easier. We don't have to worry about those spikes. From a performance standpoint, we're going to have improved ramp-up time because now the JIT server is doing all of that CPU intensive compilations, especially when the JVM needs it the most at startup. And we're going to have reduced CPU consumption when the JIT server uses an AOT cache. So if you have multiple instances of the same microservice starting up, it may be requesting compiled methods that may already exist in the current JIT server, because you can have multiple services talking to the same JIT server. From a cost standpoint, obviously, anytime you reduce your resources on the cloud, you're going to save money. And that comes in the form of actually your container provisioning and also with auto scaling. If it's very efficient, you're scaling and you only have instances for the current demand, you're only going to pay for what you need. And you're going to save money that way. And it is resilient. Like I showed in that initial graph, the JVM still has its local JIT. So if the JIT server goes away, we still have access to our local JIT. So let's talk about some performance graphs. So in this test, we are going to be looking at how JIT server is provisioned in Kubernetes setting. We're going to be using Red Hat OpenShift. We're going to have 4 different applications that we want to have multiple instances of. Let's get to the graph. This is very hard to read, but let's go through it. The top graph, the top section is without the JIT server. Each one of these colors represents a particular application. There are 4 Java enterprise applications. In this case, for example, the orange yellow one here is Acme Air monolith. We are running 8 instances. I think that's correct, if I'm counting right. We have 8 instances running, and the number associated with each square is the amount of memory that needed to be provisioned. And without the JIT server, we had to scale these up to handle those spikes. We laid that out with OpenShift Scheduler, and it laid it out this way. We're taking up 3 nodes to handle all the instances of each of these applications. Now, the bottom row here is using the JIT server. And in fact, the brown container here, these were all scaled relative to each other. As you can see, the JIT server is shown in each of the nodes. It is the largest container. Here we're showing 1200 megs. And it's handling all of these requests from all of these JVMs. And because we don't have to worry about those spikes, we were able to provision each one of these at a lot less CPU or memory size. And as you can see, we have the same number of instances running, but we only require two nodes. So we've just saved 33%. This is called application density. The more you can get into one node, the better. And if you're wondering how that performs, here we have again orange without, that's our baseline without JIT server, and the blue with. And you can see once we get to steady state, they perform exactly the same. Performance is matched with the JIT server with using 33% less resources. So we can improve container density and reduce operational costs of Java applications running in the cloud by 20 to 30%. And like I just showed, the steady state throughput is the same despite using fewer nodes. So now we'll talk about auto scaling. Here we're using the horizontal pod autoscaler. As Alex mentioned, there's multiple ways of handling scaling. In this case, typically, or one of the more popular ways is to look at CPU utilization. In this case, we set it to anytime we get over 50% CPU, we're going to spawn a new instance. Again, the orange is the baseline without the JIT server, and the blue is with JIT server. Every time you see the graph plateau like this, that means it's starting a new instance, and it's going to, CPU utilization is going to go down while it's loading that. But you can see that the JIT server spikes are less severe, and they ramp up a lot faster. And again, the main concern here is that we're not going to get any false positives because of those spikes that the autoscaler can detect as being load and starting instances incorrectly. And when that happens, it eventually is going to figure out that we don't need those, but that thrashing does take up CPU and also resources, which cost money. So now I'm going to talk, I'm going to go through a quick demo here. We're going to see the JIT server in action. So here's the setup for this. We're going to run this Open Liberty plus Acme Air application in 3 different forms. It's going to be running in a container. We're going to run it with 400 megabytes. We're going to also run it with 200 megabytes. And then we're going to run it with the JIT server using 200 megabytes. Now it has some additional containers to support this demo. The application itself uses a MongoDB. We're going to be running JMeter containers to simulate load. That is going to be stored in an Influx database, which is going to be graphed in Grafana. We also have Prometheus talking to the JIT server to get some metrics on it, which will also be displayed in Grafana. So let me go ahead and start that up. All right. So I have multiple windows here starting, and this one I think I started the Influx database, and we have Grafana running. So this is my main screen. The first thing we're going to do is start the Mongo database. Again, that is just data for the application itself. All right, now we're going to start up the JIT server. Don't worry about those messages. I'm going to start up Prometheus. Okay, now we're going to start up the actual Acme Air containers. Again, there are 3 of them. Hopefully everyone can see this. I know the font's a little small, but I do want to show you what that command does. So it's starting up each one of these.
So while this is loading, to understand a bit more, this remote JIT compilation.
It's gonna. Let me get to the show you what's in that actual script here.
Cool.
I know this is kind of behind the curtain here. So basically, if you look at this, this is our 3 Acme Air containers. We have, we're just doing Docker runs. Again, 3 different versions, one with 400 meg, one with 200 meg, and the third one also has just 200 meg, but it has JIT server options, which means it's calling out to use that JIT server, the Acme Air JIT server on this port. Did that answer your question? Or do you want more detail? Let me go ahead and run this JMeter. This is going to simulate load on all those containers. I think the interesting part is actually the Grafana graphs, which we'll get to in a second. Back, let me show. So if we look here, we have two dashboards. We have the JMeter load test. This is showing CPU throughput. Yeah, 5 minutes. So up here is the top row is without JIT server. The left one is using 400 meg. The right one's using 200. And at the bottom, we're also running at 200, but with the JIT server. And as you can see, the ramp up time is much faster with JIT server. The 400 meg will get there eventually, but it's going to take longer. And the 200 meg is never going to get anywhere. The CPU throughput is never going to be very efficient because essentially there's not enough memory to run both the application and the JIT compilations. So the JIT is smart enough to know that it's going to have out of memory issues. So it's basically not going to compile anything. So this is going to be running interpreted. So the CPU throughput is going to be very low throughout. And performance obviously is going to be very bad. So as you can see here, the 400 meg will eventually get to being fully optimized and running. The JIT server version got there a lot quicker. It ramped up faster. And again, it's using half the memory of the other container. And if we look at the other dashboard, the JIT server itself does generate some metrics. So here we're showing it connected to one client. CPU utilization when it did those initial compilations. There's available memory and the number of threads it uses. So these are all standard or performance metrics that the JIT server does produce on its own. Let's see if just to confirm, yes, this 200 meg is never going to get really started. But both of the 200 meg version and the 400 meg, 200 meg with JIT server and the 400 meg without are basically now fully optimized and running. Any questions on this? If not, I will go back to so that was just screenshots in case I couldn't get to the demo. That was my backup plan. So let's talk about how to use the JIT server. So the JIT server is just a OpenJ9 JVM. So the JVM itself can be started multiple ways. Do we have our pointer anymore? Let me get that started again. Here's how you would typically run your application. That's going to invoke the OpenJ9 JVM. You run it with a JIT server. That JVM is going to take on the persona of a JIT server. You would actually, if you're a client JVM wanting to access that JIT server, you would just use this argument here to access that JIT server. Here's some default settings for how it's used. The Eclipse blog site for OpenJ9 has a lot of good information on all the different arguments that can be used. I'm going to link to that at the end, so stick around. You don't have to remember these links. One caveat is that the Java version and OpenJ9 releases have to be the same between the client and the JIT server. JIT server usage in Kubernetes. You have to configure the JIT server deployment and the service. The client obviously are going to interact with this new JIT server service. You can configure it with YAML files, Helm charts, and there is actually an OpenShift certified operator for Open Liberty that comes with the option of using the JIT server. And it's really very convenient. In fact, I think it's just one configuration file where you just say JIT server enable and you have it. Here's a tutorial on how to use it within Kubernetes. Again, at the end, I have a link to all this. So encryption, it does work with encryption, but it does add to the network latency. Obviously, the client JVM is communicating to the JIT server through the network. So if you can avoid using, only use encryption if necessary, because it does slow down that communication. As I showed you in that previous graph, the JIT server does have a set of metrics that it provides. CPU utilization, the memory, connected clients, and active threads. It has some additional logging information, which can be very useful. So when to use it? So obviously when you're in a constrained environment, when you need to compile many methods in a relatively short time, this is when this is most useful. Obviously in a cloud setting, microservices, the problem statement we talked about earlier, this can be a solution to that. We recommend you have at least 10 to 20 client JVMs connected to that JIT server. That JIT server container, as I showed in that one container density or the application density graph, it is going to be one of your larger containers. So you have to mitigate that using that size container, additional containers. So you want to spread that out amongst a number of client JVMs. The JIT server itself should have at least 1 to 2 gigs of RAM. Also, if you get better performance if all the JVMs don't start up at the same time, the client JVMs, because if they're all accessing the JIT for the first time all at once, you're not going to get very good performance. So if you could stagger those starts, again, with the AOT cache of the JIT server, it may already have that method compiled. It can just return that. As I mentioned, encryption adds to the communication overload, so avoid that if possible. In Kubernetes, you want to set a session affinity to ensure that once a client is talking to a particular instance of a JIT server, it continues with that, especially with when you take into account AOT cache, where that compiled method already may exist. So some final thoughts. I got through this pretty quick, actually. So the JIT provides an advantage, the JIT itself. Again, it produces very optimized code, but that compilation time does add overhead. So the idea here is we are going to disaggregate that JIT from the JIT JVM, and we're going to create JIT compilation as a service. This does exist today, and it's a part of the Eclipse OpenJ9 JIT server, also known as the Samru Cloud Compiler. It's available now on Linux for Java 8, 11, 17 through the IBM Samru Runtimes distribution. It's especially good for constrained environments such as microcontainers. It is Kubernetes ready, Helm chart available, Prometheus integration, and that OpenShift certified operator. You can improve your ramp up, your auto scaling performance of short-lived applications, because that's short-lived applications spend most of their time in that ramp up time, and this can really help with that. It can reduce the application density, as we showed in the one graph, obviously reducing operation costs by 33% in our example. And the key point here is it is a Java solution to a Java problem. So Alex touched on this earlier. We talked about that hotspot, that point where we want to be the most efficient, what everyone's looking for. So there are different solutions. This one is a Java solution. It's full Java. You're going to keep your JVM. You're going to keep your JIT. All the things that make Java great, we get to keep around. We're not going to do any kind of static compilations up front where we lose some of the functionality we have with Java. So we get to keep all of that. So with that, that ends my presentation. If you scan this QR code, it takes you to a page I've created that has links to all those articles I talked about earlier, or I referenced earlier. Also contact information, so you don't have to remember this, but I'm always available, and please reach out if you have any questions. I am not a part of the JIT server team, but I have access to all those resources. So if you have any really detailed questions, I can get you to the right person to answer those. And that's it. Thank you very much. Any questions?
Thank you, Rich. I was literally about to ask the same thing. I'm just waiting to see if any questions come up in the chat. Thank you so much. That was really interesting. I love our talks for this community. I think they're always fascinating for me, and I've learned so much. So it's excellent to have you guys along to speak to us. Thank you.
Oh, my pleasure.
I am going to take it from the fact that there's nothing popping up for me in the chat, that nobody has any questions at this point. I'll just give it another moment or two in case someone's typing while I'm speaking. Okay. So I will take it that there are no more questions at this point. So all that's left for me to do is say thank you so much to Alex and Rich for coming and sharing some of what you know and sharing it with us. Thank you to everybody who's managed to make it along today. And if you're watching this online, I hope you've enjoyed the sessions and found them really helpful. And like Rich and Alex, have both said, please do reach out if you've got any further questions. And we would love to see you at our next event as well. So we look forward to seeing you all soon. Enjoy the rest of your day. Thank you so much. Take care.